on Wednesday. So we have a function called the density of states, which is telling us how many quantum states are there per unit volume of our semiconductor crystal. So this would be the total possible number of charge carriers available at any particular energy, because that's the total number of states that there would be there. But not all of these states are, these energy states, not all of them are occupied by an electron or a charge carrier. Okay, so we still don't know the answer to the question at the top of this slide, which is how many charge carriers are there in the semiconductor. We know theoretically, or an upper limit on how many charge carriers there could be, but we don't know if there are charge carriers there or not. So like this classroom, where's the fire statement thing that tells you the capacity?
Right there.
What does it say?
It actually has a number.
Fire exit?
No. It tells you the room capacity.
Oh.
No more.
No more?
Isn't
that illegal? Anyway, we can tell, right? So the number of seats in this classroom is the maximum capacity of this classroom. So that's the density, or that's the total number of states that you have in this classroom. But not all of them are filled. So if each one of you represents an electron, right? We don't say, okay, there's the same number of electrons in this classroom as the number of seats. We have to count how many of you are actually here. So the density of states is telling us how many seats there are, but not how many electrons there are yet. Okay, so we still need another piece of this puzzle, and this was mentioned in the last class as well, which is the Fermi-Dirac probability function. And this is going to tell us a ratio of the number of particles per unit volume per unit energy to the number of quantum states. Per unit volume per unit energy. So the interpretation, this is written as F sub capital F, and it's a function of energy. So the interpretation of this is that this is the probability that some energy level, some quantum state at a particular energy level is filled by an electron. That's what this probability function is telling us. And rather than deal with the probability function all the time, in your band diagrams, we represent this a little bit differently, which is by defining an energy level called the Fermi energy. So what does this Fermi energy mean?
It's for the probability you should actually have.
It's just a gauge for us to...
Not all the time. Okay, so...
Fermi energy is a level at absolute zero, all states in the valence band are filled, and nothing above Fermi or everything below it is filled and everything above it is empty at absolute zero.
Well, let's talk about probability first. So, as you know, if we're talking about probability, for those of you who took 342, you know, if something is guaranteed that it's going to happen, the probability is 1, right? Okay, so we'll say probability of 1. So the y-axis is probability, x-axis is energy, and we'll put the Fermi level on the x-axis, and I'm going to put a constraint on this, and that is that we are at absolute 0. So this is 0 Kelvin, not okay. Okay, so what does the Fermi-Dirac probability function look like?
It's a step function.
It's a step function, so
It goes to EF and then it drops down at EF.
okay, so the probability is 1 that
All the way to EF.
your electrons are all going to be at some energy level below the Fermi energy. Okay, so this is what our Fermi-Dirac probability function looks like for 0 Kelvin. And that makes sense because 0 Kelvin is, you know, the absolute ground state of the universe, right? You know, you don't have any thermal energy in anything. So it makes sense that, you know, if you look at the definition of this probability function, the number of particles per unit volume, per unit energy should be, you know, the same as the number of quantum states. So this makes sense, but we usually don't use semiconductors at absolute 0. So let's look at a different case. So we'll just say that the temperature, let's just say it's something greater than 0 Kelvin. And we look at the same probability curve. What happens to the probability curve?
K after that.
It's smoother.
It's smoother, okay? So we smooth out that step function. And what's the value?
3.
Should be 1/2 at EF.
Okay, so I know the value of that function right at the Fermi energy. It's 1/2. So the probability function looks something like that. Now, because this is a review, I'm going to skip ahead a little bit and talk about how the Fermi energy relates to our band diagrams. So here's a band diagram. Here's the conduction band. Here's the valence band. Where's my Fermi level for an intrinsic semiconductor? Exactly in the middle? It's near the middle. It's not necessarily exactly in the middle.
1.12.
That's the
So what does this mean? Given the
An equal or almost equal concentration of holes and electrons.
If it's intrinsic, it's
almost equal concentration of holes and electrons where?
I think it's depend how close do you see or EV, right?
It's in the middle.
Okay, so equal amount of holes
Then
and
it's
EV, equal amount of electrons and EV.
T equals 0 reduction.
So this is also for a temperature greater than absolute zero. Okay, so if my temperature is greater than zero and I have an intrinsic semiconductor, can I have electrons in the conduction band?
No. Well, yes.
No?
Yes.
No?
Yes.
Yes?
Yes, until it reaches 300, right? Yes.
Well, there's nothing really special about 300K except that's room temperature.
What was the question again?
If my temperature is above 0 Kelvin, do I have electrons in the conduction band of a semiconductor?
There's a chance. There's a chance. Yes.
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 Because if there isn't any electrons in the conduction band of my semiconductor, none of your electronics are going to work, because then it's an insulator, right? There's no electrons, there's no charge carriers available to move current through the semiconductor. Okay, so there is some probability I have electrons in the conduction band of the semiconductor when it's above 0 Kelvin, okay? Now the Fermi level's in the middle, so what does that mean?
There should be like an equal amount of holes on the valence band.
Yes, so there's an equal probability, because the conduction band is the same distance from the Fermi level as the valence band, just in opposite directions. There's an equal probability that my electron is in the conduction band. There's an equal probability that it's in the valence band. So that means if there's electrons, also it means if there's electrons in the conduction band, there should be some holes in the valence band. Okay, so again, we'll say temperature is greater than 0. What does it mean if my Fermi level is closer to the conduction band?
There's a greater probability to find an electron.
Where?
In the conduction band.
There's a greater probability that the electrons are in the conduction band versus the valence band. Okay, and then so if I move my Fermi level back down, then the reverse is true. So if my Fermi level is close to the valence band, there's a greater probability that the electrons are in the valence band rather than the conduction band. Okay. And you have you guys have an equation for what this Fermi-Dirac function is. We usually express it using the Maxwell-Boltzmann approximation, so that equation becomes simpler. But you've already seen that, so I'm not going to bother writing down the equation. You can refer to your textbook or your notes from last semester for the equation. This is just the physical meaning of that equation. Let's see. Okay, so I kind of went on a little sidetrack on the Fermi level. But let's go back to, let me scroll up a little bit. So I still didn't answer the question at the top of this slide. How many charge carriers are there? I know the theoretical capacity of that material for quantum states. I know the probability now using the Fermi-Dirac function that one of those quantum states, that a particular quantum state is filled or empty, but I don't have an answer. How many electrons or how many holes? Okay, so we need to take our two results and put them together. So if we look at energy, I'm plotting kind of two x-axes at once. So one is going to be the Fermi-Dirac probability function. So this is going to be plotted kind of rotated to what we did before. So at the Fermi level, the probability is a half. So right between the two tick marks on my x-axis, and then it's, you know, a curved looking function. Okay, so this is my Fermi-Dirac probability function. Now at the same time, so I'm plotting two different things right now. I'm also going to plot the density of states as a function of energy, and we saw that graph on the first slide of this lecture. So the curve at the top that starts at the conduction band energy is the density of states in the conduction band. The curve at the bottom that starts at the valence band energy and decreases is the density of states in the valence band. Okay, so I have total number of states given by density of states, and I have a probability. So if I want to know, for example, the electron distribution, then I would take the density of states and multiply that by the probability. And this graph is based on a figure in your book. I didn't write down the figure number, but you can find it after the density of states and Fermi level discussion. So it's just graphically taking those two functions, and if you multiply them together, then you get something that looks like that. And the area that I've shaded in to the left of that curve, that represents the number of electrons in the conduction band. We can do the same thing in the valence band, take the density of states in the valence band, multiply by the probability, and you get something that looks like this. So the area to the left of that curve is going to give you the number of holes. Sorry, not the absolute number. These are still concentrations. So these are a number of holes or number of electrons per unit volume. So you need to know how much of your semiconductor material that you have. It makes sense for us to express it this way because this gives you the most general set of equations, because you know, you could, let's say you're making a diode and you wanted to know the number of charge carriers in that diode. Using concentrations, you know, your diode could be any width, length, thickness, and then you just use those parameters to figure out the number of electrons. But if we made this, you know, number of electrons, then you would have to constrain the volume to a particular volume. This is more general. Okay, so the equation for the density of states contains some stuff that is going to be energy dependent, but it contains just a lot of other stuff there. So in order to make the writing of the equation simpler, we usually write the electron concentration as some constant, and you can find out the value of, if you wanted to calculate this constant, you can plug in the different values from the density of states and the Fermi-Dirac probability function. But this is something that is going to be, kind of material dependent. So once you're working with a particular semiconductor, you just use the same constant over and over again. And then an exponential term that contains energy levels and the temperature. Okay, and this is going to be the thermal equilibrium electron concentration. Since we didn't talk about doping yet, this is also equal to the intrinsic or undoped. Oops, I spelled that wrong. The intrinsic or undoped electron concentration. For holes, it's a different constant. And there can also be an intrinsic hole concentration. And for intrinsic semiconductors, we also know that the electron concentration should be the same as the hole concentration. Why?
For every, they're pairs, there's a conduction band electron produces a hole in the valence band. There's no doping. The rates of electrons going to conduction band equal the rates.
So what is a hole? Let's start with the definition of a hole.
Empty state.
Breaking bond from
It's a state, quantum state that an electron could occupy or used to occupy, but the electron is not there. So it's the absence of an electron in that state. So the hole is not a real particle. It helps to think of it as a particle to help visualize what's going on, but it's not a real particle. So if you have, a certain material and you have electrons moving up to the conduction band, then they are leaving, electron moving from the valence band to conduction band leaves behind a space where the electron was. And so the number of electrons in the conduction band should be exactly equal to the number of holes in the valence band, because those holes are just the spaces that those electrons left behind when they moved up to the conduction band. Okay, and what is the intrinsic carrier concentration for silicon? And we'll say at room temperature. What 1.5 times 10 to the 10 electrons per what? Centimeter cubed, because we're talking about density, so we're talking about per unit volume, so it should be centimeters cubed. Usually in your book, we don't bother writing electrons or holes. You just write 1 over centimeter cubed. Okay. Any questions on this so far? So now we have answered the question from the beginning of the lecture. So how many charge carriers are there? This is the concentration of electrons. So if I had a cubic centimeter of silicon at room temperature, intrinsic silicon, then I know I'm going to have 10 billion electrons in that cubic centimeter of silicon. So I know how many charge carriers there are now. And since I know how many charge carriers there are, if I put, say, an electric field across that block of silicon, then I can figure out what the current will be because I know how many charge carriers are going to be moving. Okay, so we know the answer to that question, but that's not enough yet to know to know everything that's going on in the p-n junction. One of the things that we talked about, so I'm kind of skipping around with the Fermi level, but we talked about Fermi levels. Since we're talking about intrinsic semiconductors, let's talk about the intrinsic Fermi level. So we can define an energy that's exactly halfway between the conduction band energy and the valence band energy. Just take the average of those two energies. So that's going to be the mid-gap energy. But that's not the Fermi level energy for an intrinsic semiconductor. Because of the different effective mass of the electrons and holes in the semiconductor. So the intrinsic Fermi level is going to be this mid-gap energy with a term that is a logarithmic ratio of the hole effective mass to the electron effective mass. Now, if the effective mass of the electrons and holes in your semiconductor were exactly equal, then you're going to get back the mid-gap energy. But in silicon and in most semiconductor, in real-world semiconductors, these numbers are not exactly equal. So your intrinsic Fermi level is not going to be exactly the same as the mid-gap energy. But it's pretty close. And so let's take a numerical example. So silicon at room temperature. Plug in some values. What's KT? Okay, that's a good number to remember. It'll make things faster. Okay, so holes have a different effective mass from the electrons, and we figure out this value. So this is about 13 milli-electron volts. And so the real intrinsic Fermi level is slightly below the mid-gap energy in an intrinsic silicon semiconductor at 300K. What's the band gap of silicon?
1.12.
Okay, so it's not exactly at the mid gap. So what would be the mid gap for silicon?
0.5.
0.5.
Okay, so it's not exactly at the mid gap energy level. It's at 0.0. Let's see, 4.8 around 0.0548 around there, electron volts, but it's pretty close. So the mid gap energy is a pretty good approximation, which is why if you draw if you have a band diagram, you're just sketching the band diagram and you draw the intrinsic Fermi level about in the middle of the conduction band and valence band energies. That's a pretty good approximation. But it's not exactly the same. Okay. Let's go back a little bit. So we have for our intrinsic semiconductor, we figured out the number of electrons available per unit volume. But this is for our intrinsic semiconductor. We don't have to be stuck with this particular number of charge carriers per volume in our semiconductor. We can actually do stuff to the material to make more charge carriers or more or less charge carriers available in our semiconductor material. So what is that called? Doping. Okay, so doping of semiconductors, it's different from like doping in the Olympics or something like that. So we're going to be adding atoms that have either more or less valence electrons. So add atoms to a semiconductor that have more or less valence electrons than our semiconductor material in order to adjust that concentration of electrons or holes. Okay, so if we're talking about or when we talk about doping, we can talk about doping with donor atoms. These have extra electrons compared to silicon. And what are some examples of donor atoms? Phosphorus, yes. Boron, no. So acceptors, these have less electrons. Maybe let me. So boron is a dopant, but it's a p-type dopant and it has less electrons. An n-type dopant that has more electrons, arsenic is one, aluminum is another, p-type. So we can put these different atoms into silicon in order to adjust the concentration of electrons or holes. So if we do that, we have new we can use new equations for the concentration of electrons in holes. And this looks similar in form to the previous electron concentration equation, but notice that we're referencing everything relative to the intrinsic concentrations. So this first term, n sub I, this is the intrinsic electron concentration. We're referencing the new Fermi level of the doped semiconductor to the intrinsic Fermi level of that semiconductor. And same thing with holes. And if you multiply the two concentrations together, it should equal to the intrinsic semiconductor carrier concentration. But the electron and hole concentration do not have to be equal to each other anymore, because we added these atoms that are not silicon in there. So we changed that that chemistry of the material so that we don't have to make that assumption anymore. Okay, so by adding these dopant atoms at various concentrations, we can change the carrier concentrations as well. Now there is a case, a more extreme case of this doping where you can end up with something called degenerate doping. This is sounding more and more like illegal drugs. But what does this mean in terms of our semiconductor doping?
Excessive doping, right?
Heavily doped. Okay, so why would you want to do that, or what's the definition of this?
Does it become degenerate when the Fermi energy is either in the conduction band or in the valence band?
Yes. Okay, so this is when you have a very high concentration of dopants, high enough that the Fermi energy is in the conduction band, or the Fermi energy is in the valence band. Why would you want to do that? Make a semiconductor very conductive. It doesn't make it very insulating. So we're putting a large number of charge carriers available to where we need them, where we need free charge carriers available to conduct charge through the material. Okay, so this is making the semiconductor look more like a metal.
Is that P or N type?
More n-type and
Yeah.
more p-type, I think something like this.
Yeah.
Yeah.
Okay, so this is N-type,
Super N type,
That's why they use silicon.
yeah.
and this is P-type.
So does N-type make it more conductive? And
Yeah.
P-type makes it less conductive?
No, they're both conductive.
I think this hot silicon can be right, like it can be the acceptor donor, that's the one. Something like this.
Well, silicon is usually the base material. This applies to any semiconductor, though. Any semiconductor that you can add doping atoms to. Okay, so my semiconductor can become more like a metal. There's a large number of free charge carriers, so it can conduct electrical current very easily. Why would I want to do that?
The high current.
Okay, so it becomes more like a metal in that. Let me put it in more technical terms. So it's more conductive. So why would I want to make a semiconductor like a metal?
Just in case or something.
Just in case. just in case.
What if we need it for something for that application
Is
wise?
it like a metal?
Yo.
You can control the current more easily, but you would still need a lot of it. So it's like a metal, but you can control it easier. Do you like that?
Professor Martin told us, but I don't remember.
Not quite.
Maybe if you want to make your devices smaller and smaller, if you want to make your devices smaller and smaller, and you know you need to control the flow of charge within that device, you don't need a bunch of external components to do it.
Super metal.
Who took 323 already? Or is taking it? So this is the structure of a MOSFET transistor. There's an oxide there. That's what the O in MOSFET stands for. And depends on what kind of transistor this is. Let's say it's a N-channel MOSFET. So the substrate is going to be P-type. You're going to have these wells for the source and the drain. And what is the gate?
That's the middle part.
This is the metal part. So this is the metal gate, the M in MOSFET, but it doesn't have to be metal. Same thing. When we also need to put some contacts here and here. You know, this becomes your drain terminal and your source terminal to the MOSFET. But these connections here don't have to be metal as long as they're conductive. So you don't have to do necessarily have to do metal deposition to get these electrical contacts here. You can just use a very highly doped semiconductor at that surface because it will be conductive enough. So it gives you some more options for making, for the actual fabrication of the semiconductor device if you do this degenerate doping. Okay, where are we? Okay. Let's go back up to here. I forgot to write down what the Fermi levels are in a doped semiconductor. So this difference between the Fermi level and the intrinsic Fermi level . Actually, this is kind of circular. It's just some algebra on the equation on the left. but one of the important insights that we can get from looking at the Fermi level equations the way that it's written on the right side is that that Fermi level is going to be a function of temperature, right? And that's what we figured out anyway, intuitively, because we looked at the temperature equals 0 Kelvin and temperature above that. So we know the Fermi level is a function of temperature, and this is just reinforcing that. So what does that mean in terms of your electronics if the Fermi level is a function of temperature?
It's gonna break.
It's going to break? Well, why?
It's too hot.
If it exceeds
It might break, it might melt.
it can break.
Why would it melt? Why would it melt if it gets too hot?
Or more energy being used.
Well, let's not change the amount of energy. So you're going to still use your same electronic device, your same transistor, your same diode, same whatever. You're just going to use it at a really high temperature. What happens to it?
Everything becomes open and
So many bonds.
It's gonna melt. All the bonds are gonna be broken.
Can break
Like
more
the-
bonds, and then that level.
Well, I'm not talking about actually burning it up or like not that high a temperature. But okay, so what happens to? Let's say I have an N-type dope semiconductor. So what happens to my Fermi level as temperature increases?
Oh, it's gonna be closer and closer. No.
it gets to
Does my Fermi level increase or decrease?
No, it's decrease.
Increase.
Increase. So if my Fermi level increases, what does that mean?
That
There's more energy, or more electrons
More electrons where?
in the conduction.
In the conduction band. So I can start conducting more current through my semiconductor. I didn't do anything except change the temperature. Like if you had a voltage across it, same voltage. But now you're getting more current because the temperature is higher. Because now you have more electrons going in the conduction band. Okay, so if your circuit that has this semiconductor has something else that's sensitive to a high amount of current, if the temperature goes up high enough, right? You're going.
It's gonna melt, break it.
Well, this is really extreme temperatures. You might damage something else in your circuit, right? So if you're designing electronics that are, say, made for space, they're made for some extreme temperature environment, you have to be considering these kinds of things. So just remember that it's there. Most of the time we're just going to be assuming room temperature because that's the nice temperature that we like. But every time you look at an equation, you have to and every time we simplify an equation, you have to say, okay, why are we simplifying it? What assumptions are we making? And when you reuse that equation, for a particular situation, can you still use those same assumptions? Okay, so we're going to end here for today.